Uh, so I gave an overview of what stars are like, not yet how they work and what explains these patterns that we see among the stars. We had a sense that the more massive stars are much more luminous. The luminosity goes up a lot faster than the mass, so they don't last as long. But we didn't explain where everything was. Now, there's another part of what we see out there in the galaxy that's not the stars. And what that is we call it, very imaginatively, the interstellar medium, which means the stuff between the stars. So if it's not stars, it must be the stuff in between. So, and the reason we have to talk about the stuff in between is because it's from this that the stars form, and when the stars die, the material that makes them up is returned back to the interstellar medium. So this is where we're going to start the story of how stars are formed and then evolve. We'll start with the gas from which they come from. So first of all, we'll talk about, well, what exactly is in the interstellar medium. And then there's certain parts of the interstellar medium that are quite pretty, that light up, and we call those nebula, which just means clouds. And we'll understand why they light up and the different possibilities. And then we'll talk a little bit about, as these clouds get more and more dense, what's going to happen to them. So this deserves lights out. It's so much prettier there. Let's see, we'll do that one maybe. Maybe not. Okay. So this is just a picture of the Milky Way. It actually was taken by a guy who was well off, who went around the world with a 35 millimeter camera, digital camera that was on a mount, so it could track the sky. So this essentially is, if your eyes were much more sensitive and you were in a dark place, this is what the Milky Way would look like to your eye. So this is going all the way across the sky. So normally you just see, at any one point on Earth, you'll see about half of this, because it'll go from over to there. First of all, it's really pretty. So let's see a few things that we'll notice, is that the stars are sort of concentrated in this band across the sky, and this is just the disk of our galaxy, and we'll talk a lot more about that later when we talk about our galaxy. And we'll see there's a lot of stuff here that's the color of stars, like kind of white. This is a cluster of stars. But then you'll see other colors. We see some reds over here. You see the reds. It's a bit of green in here you might see, but I don't think that's too dramatic. It's this purple. But then there's all of this stuff. This black, right? Which is dark parts of the sky too. And this black and also these glowing parts we're seeing evidence of this glow of the interstellar medium, right? Of the stuff between the stars, because the stars are generally this color, more or less. So inside the interstellar medium, in between the stars, there's gas and dust. And what I mean by gas is it's mainly hydrogen and helium. And if we had a box the size of a die, so 1 centimeter on a side, in the interstellar medium, there'd typically be one atom in that box. Okay? So it's really, 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 really empty, the interstellar medium. Right? So if we were to think of a little box, let's say, of this size of water, like a little box of water, there'd not be one atom in there, but there'd be something like 10 to the 23 atoms in there, okay? So the space between the stars is 10 to the 23 times less dense than water. It's really empty. It's much more empty than anything that we can make on Earth. We can't take the atoms away. So the best we can do on Earth is 10,000 times more dense. So 10,000 molecules per little box. Now, what we call dust isn't dust like we have in your house. Do you know what dust in your house is mainly? Kind of gross. It's your skin. That's not interstellar dust. But interstellar dust, you want to think of it, a good analogy is something like soot or smoke. And it's often literally that. It's bits of carbon that are all stuck together. And there could be bigger clumps, but typically they're quite small, meaning a millionth of a meter in size. Now, if we wanted to find these little dust particles, you'd have to look on a cube 10 meters in a side. Right? So this room, if it were in space, every cubic centimeter would have an atom. So there'd be a lot of atoms in the room. Not compared to what they are now, but there'd only be one particle of dust. And that's pretty much what there is. But that has these two things. Space is really, really big. So when we think of looking over large volumes and large distances, it does add up, right? Even though any location, it's very, very not dense. I'll turn the lights on. There'll be more pretty pictures, though. So if I were to gather, for example, all of the dust in the volume of the Earth in space, I could make a cubic centimeter of dust. So that huge volume, if I gathered all those bits of solids that are in the interstellar medium, I could compress them into a dye. So it's really, really empty. Really, it's nearly completely empty. But this dust has a profound effect on what we see. So let's imagine we have some light going past the dust, and this is purple light. So the purple light is maybe about the same size as the dust particle, and it can really interact quite nicely with the dust particle, whereas red light is much bigger, so it doesn't interact. So like an analogy of this is like, let's say you're going on gravel on inline skates. That's not going to be comfortable. You're not going to roll. But if you drive over it on your car, it's no problem, because the skate is about the same size as the gravel, but the wheel of your car isn't, right? It's much bigger. So the light that has a longer wavelength doesn't interact with the dust so much. So like an example here on Earth, if you think about it, if you look down at the sunset, the sunlight is passing through actually a lot of dust that's in our atmosphere. And the sunlight, as it sets, the sun as it sets looks red, right? And that's because the blue light that's in the sunlight gets scattered by the dust and other components of the atmosphere, whereas the red light passes through. So in a certain sense, when you see the blue sky, that's blue light from the sun that has been taken from someone else's sunset and scattered into our line of sight, right? So all the light ends up adding up, right? So the blue sky, the blue light of the sky also comes from the sun, and it means someone else had a redder sun, and they have a redder sunset. So it's the same thing with this dust, that the dust will interact with the red light less than the blue light, and I'll show you what that looks like. So if we look at what this dust actually looks like close up, there'll be some little chunk of carbon or a bit of sand, if you think of that. And then on top, we'll freeze on top water and ammonia and methane. So like the reason it looks like this is these are the most common elements in the universe other than helium. So they form little molecules that can freeze onto these little grains. And then they interact with the light. So here's a picture, right? So this is one of those dark regions of the sky, but we've zoomed into it. It's an interstellar cloud. It's called Barnard 68. So I'm going to turn off the light so we can see it a little better. Maybe we'll turn off the light. Maybe it'll work. Maybe I'm impatient. So on the left-hand side is a visible light picture of that. Is an invisible light, and we can't see through it, right? And you look over here, and the stars look kind of normal, but over here, look, the stars over here are on average a bit redder than the stars over here, right? That's because the cloud extends over this region, but it's not so absorbing so much light, or that you can't see it. All it's doing is it's absorbing the blue light much more than the red light, so those stars look red. Now, on this side is the same part of sky, but not looking with what we see with our eyes, but in infrared. And there you can see, yeah, there are stars back there. Look at that. They're behind the cloud, but they're like the bluer components, in this case, the shorter wavelengths of infrared light are absorbed more than the longer wavelengths. So even in the infrared, the color is shifted towards longer wavelengths by the absorption, right? So if we look over here, again, we see at the edge of the cloud, there's less reddening, as we call it, and as we go to the center of the cloud, there's more reddening, right? So how can we tell, though, what's going on? Like, you could argue, well, maybe these stars over here, for some reason, are just redder stars. They're cooler stars. Their colors look like a cooler star. But the key is, if you remember, we had two quantities we talked about with stars that were they usually went together. One was spectral type, which you got by looking at what spectral lines were excited, and the other was color. Well, guess what? The same spectral lines are excited. This reddening doesn't change the strength of the lines. It just changes the gross color of the light. So you can tell that this star in here, although it looks kind of redder than one of these stars, inherently it's the same type of star. So we can make sure it all makes sense. So we can figure out how much reddening is in different parts of the sky. So here's a picture of what's going on. The light from the star, the longer wavelength light doesn't interact with the dust so much, and we get it over here. And the shorter wavelength light gets scattered off to the side. Okay? So you can ask a question like, let's say this star was super, super bright, right, over here. Someone over here wouldn't see that star. They could see it straight like that. There's the star, right? But they'll also see light from the cloud that was scattered by the star. So they'll see that the cloud will light up in bluish light. And we'll see pictures of that in a little bit. Okay? So, and if you look straight through, it's red. So this analogy is sort of like the Earth, right? This could be the Earth's atmosphere. Here's the sun, and it's sunset, so you're looking through lots of atmosphere. The blue light of the sun is scattered. The red light passes through. I see a red sunset, but somewhere else on Earth, they'll see the blue sky. So this is one way that we see evidence for the interstellar medium, in the fact that the dust, even though it's not very common, it interacts with the light, and it makes the colors of the stars behind it redder. Here's another red color, right? And this is in the Orion Nebula. And if I look at if I take a spectrograph to this red color here, it's not coming in all colors of the rainbow around red. It's just coming in a particular line of hydrogen. In fact, that line that we talked about a while ago, where the atom is going from the third level, now it's falling down to the second level, it will emit red light. And what we're seeing here is just that red light, which is telling us that what's happening here is that the stars in this nebula are so bright and they're emitting very high energy light that's enough to take the hydrogen atom and rip the electron off. Okay, so now I have ionized hydrogen. This electron, what it's going to do is it's attracted to the proton. So it will fall back occasionally and rejoin with the proton. That's fine. But let's say it falls all the way down to the bottom level. It'll emit a bit of light that's enough to make another electron escape. So that light will now come out of this nebula. On the other hand, let's say it doesn't fall so far. It falls not to the bottom level, but to the third level. That bit of light will go do something. But then it goes from the third to the second, and it'll make this red light. So what's happening is this red light is indicating that electrons are being stripped off the atoms and then falling back onto them again. And when it falls from the third level of the ladder to the second, it makes this red light. So this is the Orion Nebula. So what's exciting the gas to make it glow is just these bright blue stars that are in here. So this sky you can see with your eye, right? You can see it as a fuzzy patch in just below the belt of Orion. So here we have another example of something of a familiar thing in the sky, which is the Pleiades. So here we have all of this stuff over here is glowing blue. Right? So why do you think it's glowing blue? Or why do you think it's blue? Pardon? Shorter wavelength. So like if I were to measure the spectrum of this blue light, would it have lots of lines like the red light, or what would its spectrum look like, do you think? Any guesses? Like, remember, with the red light, it wasn't all colors of round red in the rainbow. It was just a particular wavelength that hydrogen was doing. Here, what's happening is something else. And I told you what it was a few minutes ago. Does anyone remember? Yeah?
Is it the light coming off stars from another direction?
Yeah, so this stuff is, let's say this star sends light directly to us, but it also sends stuff off to the side a little bit, and it interacts with some dust and gets scattered towards us. And if you remember, the light that's scattered is the bluer light. So that's why this is all blue. And if I were to take the spectrum of this blue light, it's just the light scattered off the stars. So it would look like the spectrum of a star, not of hot, diffuse gas. Does that make sense? It's going to be the bluer part of that spectrum will be more important, but it'll look like, sort of like a star spectrum that's, like this star might be behind a lot of dust. I'm not sure. These yellowy stars could be behind a lot of dust, or they could be just stars that have evolved a little bit. But this glowing is due to the blue light of the stars getting scattered by the dust. So this is called, the first type of nebula we talked about, Orion, is called an emission nebula. This is called a reflection nebula, because we're seeing the evidence of a cloud, but we see the cloud from the scattered light. Really, just like the clouds in our sky, right? We see that they're there because light gets scattered by the cloud. Here we're seeing light scattered, in this case by dust, and that's why it looks blue. All right? So the blue around the Pleiades is light reflecting off of the dust, right? So the dust scatters the blue light from the young stars. Okay. So we can see the dust. We can even see often that sometimes the dust looks really pretty. So this is called the Horsehead Nebula. And you can see we have trouble down here. You know, this is really dark. And then we look down below, and it looks quite dark what's going on. And this is in the visible light. If we look over here in infrared light, we can see through this cloud of dust, and we see that there's lots of hot stars back in there, right? So here there's some hot star here that's making this glow. If I look at the actual little horse head, it doesn't look so much like a horse head anymore. And this cloud is actually, there's lots of stars embedded in the cloud. This is a region where there's young stars in a cloud. So this gives us a hint, right? Where are young stars being born? In these clouds of dense gas. So we can see the dust. And if we go to long enough wavelengths, we can actually see the dust glowing itself. So this is showing the Milky Way now in visible, what we would see. And this is showing not how much the dust is absorbing, but the dust heats up. So if the dust is in around these young stars, it'll heat up to maybe 100 degrees or so above absolute zero. And like anything that's hot, it glows. But instead of glowing where we can see, that would be 5,000 degrees more or less, it glows at a wavelength 50 times larger because the temperature is 50 times smaller. So this is glowing not around a millionth of a meter, but around 50 millionths of a meter is the wavelength that we're talking about. So we can see where is the dust hottest and where is it most excited and where is it thick. So this is the glow of that dust. So it's measuring the temperature of the dust itself. So we can see the dust directly and we can see it blocking what's going on behind it. So here's an example where we see a whole bunch of things combined all at once. This has a whole bunch of things in it that are quite cool. So this is a star called Antares down here. And Antares, there's the constellation Scorpio, which is never very high in the sky here, but it's the highest in the evenings of the fall. It's very in the far south. And if you look at it, it looks like a scorpion, right? It has a big tail, Scorpio. And there's a red star that you can think of as the eye of the scorpion, and that's Antares. So if we look in that direction, this is a very large star that's a red supergiant. And there's lots of young stars around here, so we can see these young stars there's light being scattered off of the dust around there. We see these dust lanes where it's more dusty and the light isn't scattered, but we're seeing it absorbed. This guy is a cluster of stars called Messier 4 that's behind all of this stuff. So we see a real complicated picture of these young stars that are embedded in these dust clouds. We can see somewhat here maybe we see a bit of glow from that dust cloud, from the gas rather. So it's a funny sort of greenish color. And we also see the light that's reflected by the dust as well as absorbed. So we see a whole bunch of stuff going on. Now, there are other colors that we see. So this is a famous picture. They call it like the Pillars of Creation. But this is in the Eagle Nebula, and this is taken with the Hubble Space Telescope. It's actually changed. Like this might have been taken 15 years ago. It looks different now. Things actually change in the sky on that time scale. But then here the question is, there's all this blue, this green color here, right? So we talked about the red from hydrogen. the next big color that shows up in nebula is green, it turns out. It's green. And it's kind of funny. You have to think about what it is. So if one looks around through our table here, there aren't any common atoms that in the laboratory make this color green. So it took them a while to figure it out. Initially, when they first saw it, they called it nibellium, like the element that's in the nebula. And they thought that was a win because they saw this helium, and hey, it was a new element. The line in the sun that we never saw was a new element. This isn't a new element. In fact, this color, has anyone ever seen the Northern Lights? Or seen pictures of the Northern Lights? Few of you? A great way to see the Northern Lights is on a plane, actually. Like if you're flying to Europe in the middle of the night, you get up and look, because it's almost guaranteed. But that Northern Lights have that color in them too. And what it is not any new element. What it is just oxygen. Oxygen that's been ionized, and you don't see it in the lab because it takes a long time for the oxygen atom to emit this color of light. So what happens if I do it in the lab, you get the oxygen excited and it's ready to emit this color of light, but then it waits a while, and another atom runs into it before it has a chance to do it. Whereas in space, of course, it's really empty, so the atoms don't run into each other. So this guy is just oxygen that we're seeing just glowing from the bright light of the young stars nearby. Okay? So if we look at what makes up interstellar gas in terms of, if I count the atoms in interstellar gas, 90% of the atoms are hydrogen, about 9% is helium, and 1% is everything else. That's if I'm counting atoms. If I think about by mass, it's going to be around 70% because hydrogen doesn't weigh so much, and 28% this and 2% that. So the way we can tell what's in the gas is I can look at a star and the light going through the gas. I can see the absorption lines from the star, but if that star is passing through the gas will also add its own absorption lines on top of that of the star. The difference is the star is hotter, so the absorption lines are broad, right? The absorption lines in the star are formed in some gas that's maybe 3,000 or 4,000 degrees, or maybe even hotter, whereas this gas in here is very cold. It could be just a few hundred degrees. So we'll see, in addition to the broad lines, narrow lines, and we can measure these narrow lines, and they don't appear at the same place because the star is moving relative to the gas cloud. So there's a little Doppler effect. So we can measure what's in the cloud. That's how come we know that, right? What fraction of different things. Now, if you thought about it a little bit, the composition of these gas clouds is almost exactly what the composition of the sun is. Okay? It's not like the composition of the Earth. The Earth is not 90% hydrogen. It's the composition of the gas in between the stars is essentially the same as the stars themselves. So there's another way to measure the gas between the stars. And we really just talked about how we see the presence of the gas mainly because of light passing through it, or the gas gets heated up by a star and glows. But the gas itself, especially the most common gas, which is just the hydrogen gas, it emits radio waves all on its own that we can see even from galaxies from hydrogen gas on the other side of the universe. And it's kind of simple what's happening. This is a picture of what's happening. So the atom, there's a proton in a hydrogen atom and an electron. And they're attracted to each other by the fact that this is positive and this is negative. And that's why one orbits the other. They're pulling together. But both the proton and the electron, not only do they have this electric charge, they also are little magnets. They have a little magnetic field with them. Now, if you remember, if you take a magnet like the north and the south of another magnet, they like to line up, like north to south, and so on. So what you could do with the little magnets in hydrogen gas is they could be pointed in the same direction or they can be pointed in opposite direction. And when you flip, if you try to flip a magnet over, it takes energy, right? So there's a difference in energy between whether the magnets are lined up or not lined up. And when it flips from one way to another, some energy is released. And that energy comes out as a radio wave at 21 centimeters. So 21 centimeters is like 1.5 gigahertz. So it's like just around where your cell phone operates, unfortunately, but it's a bit lower than that frequency. So we can measure this radiation from the gas throughout the galaxy. And this shows a picture of it. So this is as we're looking across the Milky Way. So this is looking towards the center of the Milky Way and looking directly away from the center in either direction. And what's going in the other direction is showing how the gas is moving relative to us. So not all the gas is stationary relative to us. That would be 0. And you can see, let's see if there's some pattern. There's this pattern that looks like a sine wave, which isn't a coincidence. But the gas in the galaxy is all moving around. And we'll talk a little bit more about how it moves around when we talk about the Milky Way. But we can actually hear, this is just the most common gas in the galaxy, just the hydrogen gas that's not excited, it's not in a dust cloud, it's just sitting there. And so we can measure the total gas that's between the stars like this, and we can get a picture of what the galaxy looks like. So we have the gas in different sorts of components. We have the gas that is just neutral gas, this hydrogen that I just showed you. And occasionally there would be parts where that hydrogen gas is a bit more dense, and let's say there's some gas, some hydrogen gas, there's some dust. Remember that things like to stick to the dust. So let's say one hydrogen, if I'm a hydrogen atom, it's going to be a long time before I bump into another hydrogen atom. Remember, it's very diffuse, and if I want to actually join up with another hydrogen atom and make a molecule, I need a third one to take that energy away because I'm making a molecule. So what actually happens out there in the gas is these bits of dust particles are like signals bars, right? So one hydrogen atom will land on the dust, and then another hydrogen atom will land on the dust. The two will get together and pop off and form a hydrogen molecule. So when the gas starts getting dense, what will happen is the atoms of hydrogen will land on the dust and form molecules. So as the gas and dust gets more dense in a certain region, you form molecules. And once you start forming molecules, whether it's of hydrogen or here of the next most common molecule is carbon bound to an oxygen, because they're very common elements out there. Those molecules, even though the gas is cold, they can emit radiation again, right? And so then the gas gets cooler and cooler and denser, and sort of runs away with itself. So once you start forming these molecules, that region becomes even more dense and even more cold with time, and that's really important.